So good afternoon. This is lecture 13, the final lecture of this summer course entitled Using Vector Calculus to Solve Problems in Electricity and Magnetism. My name is Dr. Richardson, and my point of contact email is listed on this slide. A couple administrative issues. Again, please remember that learning is not a passive activity, that to grasp the concepts and their applications, you have to take notes throughout the lecture, not just sit back and watch me write things on the board. You'll get nothing out of this summer course unless you do the problem sets. And problem sets are all available in the appropriate space in the Google Drive, as long as also accompanied with detailed problem set solutions. And again, the general idea is don't just simply skip and look at the solutions and try to work backwards. If the problem is challenging, put it to the side, come back to it later. You can look at a solution and just highlight one line at a time just to get a hint, but you'll learn more that way. Ask questions. I'm available with the email address above, and you'll need a ruler to draw the appropriate figures and diagrams, both in lecture and in doing the problems. So I want to say something more about electrostatics. And I want to go back. We were a bit sloppy with some, not all, but some of our notation. I want to go back and do a little bit more carefully at times, not all the times, not all the time, but at times. So the bad news. The good news is that we managed to do all problems, both in lecture and in the problem sets, correctly, despite the sloppiness at some points with the formalism. Okay, so let's go back to the beginning. Look at Coulomb's law. So again, if you have a charge Q and another charge Q prime, and these two charges are tacked somewhere in space, so they're fixed, and let's say they're separated by some distance r, then Coulomb's law says that there's a force between these two charges. It's proportional to the product of Q and Q prime. That force goes like 1 over the separation distance squared. That force is radial, where I write the unit radial vector r hat, and of course it's defined in a normal way. The unit radial vector is just the vector r divided by its magnitude, length, or norm. So in this particular illustration or figure, the charge Q is at the origin. So we have set this up so that we have written Coulomb's law, assuming that Q was tacked at the origin. We could have done the same thing if we tacked Q prime at the origin also, but both expressions would be the same. So the reason why this is important is that you could write down a general expression for Coulomb's law where the origin is anywhere. It doesn't have to reside exactly where a charge is. So what am I talking about? So suppose I have a charge Q and I put it at a distance r, with respect to some origin. And then suppose I nail, again, this is electrostatics. These charges are not moving, they're fixed. And then I nail down another charge, Q prime, and its distance from the origin, I'll call R prime. So I can now define a vector R minus R prime. That vector, using the appropriate rules of vector analysis we looked at many moons ago, has to point in that direction. And now I can write down my general expression for Coulomb's law. Note that when I add R and R minus R prime, actually the vector points in this direction, sorry. I do my vector addition correctly. Right. So R minus R prime added into R prime gives me my vector R. So that's the right direction. So now I can go back to Coulomb's law and write it a little bit more generally. Namely, it has the same product in the numerator. It has 4 pi epsilon naught, where epsilon naught is the permittivity of free space. But in the denominator, I now have R minus R prime squared. And the numerator have a unit vector, R hat. So R hat is in the direction of this vector R minus R prime. But the key point here is, unlike in the previous case, I need not put the charge at the origin. This is a much more general way of writing down Coulomb's law. And again, we saw lots of applications where you don't like to have unit vectors in the numerator. So what you can do is get rid of that unit vector in the numerator by just putting R minus R prime upstairs, and you pay a price. You have to change the denominator. It is the length of that vector R minus R prime cubed. So that's a much more powerful or general way to write Coulomb's law, where you're not restricting that the charge reside at the origin. Okay, so if you're going to insist on using this more general form for Coulomb's law, then you've got to be consistent with your electrostatics. So again, let's go back and look at the electric field. Remember, we define electric field as a vector. It's a vector field. It's just a force divided by the test charge. So here's my charge Q. And away from that charge Q is some point in space where there used to be a charge Q prime, but I eliminated. But there's still something going on at that point in space. The thing that's going on at that point in space is the existence of a vector field, or an electric field, which actually has momentum and energy. And it is simply Q divided by 4 pi epsilon naught, when we do the division correctly, times R hat. And again, there are lots of examples where unit vectors are not very helpful, especially when you have to integrate over them. So you can replace the unit vector in the numerator by the vector R. And you just get that expression for the electric field. But again, here the charge is at the origin. Okay. So both of these correct expressions are correct for calculating electric field of a point charge, assuming the point charge is at the origin. And you may say, well, shouldn't you always do that? Well, not necessarily. You could, let's draw a new diagram. You could imagine a case where you decide to put the charge Q here with respect to the origin. And so what you will do to tell the audience where that charge is you will define a vector R prime. R prime is something which we'll call a source vector. It tells you where the charge is. And now the question you want to ask is where, or what is rather, the electric field at R? And so we're going to call R the field vector, because after all, it tells us where the charge is, or where the field is that you want to calculate, namely the electric field. And again, note here in this more general form that the charge is not at the origin. So again, there has to be a vector that points. Now you see why vector analysis helps you get this right exactly, from the charge Q exactly to the point at which you want to calculate or measure the electric field. And that vector is R minus R prime. So in this case, the electric field is a vector field. It points in the R hat direction. So R hat is in the direction of the vector R minus R prime. All consistent. I have my ubiquitous factor of 4 pi epsilon naught downstairs. But now I have the norm of the vector R minus R prime squared. And again, if you want to write this in a more general form, where you don't want a unit vector in the numerator, we saw that that's extremely useful for lots of applications, especially when you have to do tough integrals involving vectors. You can do that, you just have to alter the denominator. So this is a much more general way to write down the electric field for a point charge. And again, we use this idea of limiting cases. Note that in fact, if R prime were 0, you would get back the previous result. And then you get the same result that you would expect if the charge were at the origin. So again, you may say, well, fine, I just have 1 point charge and really shouldn't be a big deal about whether I put the charge at the origin or someplace else with respect to some origin. Well, here's where it makes a big difference. If you have multiple point charges, then you can see why this general description of Coulomb's law and the electric field is going to be useful where the origin is anywhere. Because if I have a system where I have, let's say, I don't know, 3 point charges, they're fixed, I'm doing electrostatics, and let's say my origin is here, here's the x-axis, here's the y-axis. So I'll construct a position vector. I'll call this R sub I prime, or in this case, let's clean it up a little bit. Well, in this case, the subscript I is 3. Now you see where this generalization is going to be more useful. Because if you want to calculate the electric field at some arbitrary point R, so remember, R sub I prime is what we call a source vector. Tells you where the charge is actually located. In this case, I put in the subscript I because I have 3 possible positions of where to put charge, 1, 2, and 3. R is, again, just the field vector. Tells you what position you want to calculate or measure or evaluate the electric field. And let's clean things up a bit. So this is Q sub 3. And so I can construct a vector that goes from Q sub 1 to R. Let's write that a little bit more carefully down here so we can see what's going on. Yeah, that's much better. So here's my origin. Here is R prime sub I. That's my source vector. Here's my field vector R. And this vector is R minus R sub I prime. And my charge Q sub 3 is here. And this is the point where I want to evaluate the electric field. So what is that? Well, again, I just take what I wrote down before and generalize it. What I have to do is add up. The principle of superposition always helps. So I add up the contributions from all of those point charges. And again, I have my factor of the length of R minus R prime. So this is prime, and this thing is cubed. So you may say, well, shouldn't the electric field go like 1 over R squared? Well, it does, right? Because the numerator goes like M, a length. The denominator goes like a length cubed. So the net effect is that this thing goes like 1 over a length squared. So this is complicated. Formalism is a lot more complicated. That's the bad news. The good news is it's going to help you clean up some things and get some things right carefully when you need to. So I want to go back and look at a problem that we talked about. Lecture 5. And again, let's draw the system first. Define all the variables, and we'll discuss the physics in a minute. So here's a charge Q. Here's another charge Q. I'll do this so my unit vectors are pointed accordingly. And here's a point P. Again, this should be very familiar to you. There's a distance from P to Q there. There's a distance from that charge. And Q are separated by a distance D. So if I place my origin there, the distance from the origin to each one of the charges is just D over 2. So the question we asked, given 2-point charges, given 2-point charges, Q and Q, both are the same. Find the electric field at the point P. That was the problem we wanted to solve. So let's call this charge Q sub 1. Let's call this charge Q sub 2. And the genesis of the solution is just realizing that principle of superposition is in play. Just calculate the electric field due to Q sub 1, calculate it due to Q sub 2, again, acting at point P, and add the results together. Well, we went ahead and did this problem. And we wrote down this expression, Q over 4 pi epsilon naught, R squared times the unit vector R hat. And again, in this particular problem, Q was Q sub 1. Well, if you think about it, there's a problem here. This expression for the electric field is not applicable, technically speaking, exactly speaking, to this problem. because neither one of your charges, Q1 or definitely not even Q2, is located at the origin. So I'm going to revisit this problem, and I'm going to do this with the general form that we just discussed for calculating electric field, where the origin and the position of a charge are two different things. So a charge is not necessarily at the origin. I'll get the result that we got, and then I'll come back and show you that, in fact, if we go back and look at see what we actually did, even though we used an expression which technically is not right, we made another assumption that got us back on track. So essentially, we went forward, we were going forward, we went backwards by one step, and then we went forward and got back on the right path. Okay, so let us keep our figure. And again, I'm just going to do this, set this problem up for Q1. When we finish, you can certainly apply this to Q2, and everything's going to be the same. So the general expression that we should write down for the electric field due to Q1 is that it's the Q1 divided by 4 pi epsilon naught times r hat divided by r minus r prime squared. Excuse me. Or if you want to get rid of my unit vector, there are lots of cases where we saw that we didn't want to have unit vectors in the numerator when we actually sat down and looked at applications and doing these integrals. You can do that, you just have to modify the denominator. So let's look at this diagram. So what we need to get from this diagram is an answer to the following question. What is r minus r prime? What's the difference between the position vector r, or the field vector r, and the source vector r prime? Okay, well, I am going to look at my figure and pull out that information. I'll do it down here. So I don't want to make my figure too complicated. So we always got to pay attention to the origin. Where is the origin in this problem? So in this problem, the origin is right here. There is a vector, which is r primed, and it goes right to where the charge is, Q1. There is another vector, r, and she goes from the origin to the point P. That's where you want to calculate the electric field. This vector is none other than r minus r prime. So in fact, in this problem, r minus r prime is a vector that starts where the charge is, specifically Q1, and ends up at the point in space where you want to evaluate the electric field. So you can write all this out. We can do that here. Clearly, r is a vector that goes in the positive z direction and has magnitude z. R prime is a vector that has magnitude x, and it points in the positive x direction. And in this particular example, x is just d over 2. It's a distance from the origin to where the charge is. So we can write down an expression for r minus r prime. It's just minus d over 2 I hat plus k hat z. And let's make some room. So I need two things. I need to know two things. I need to know what r minus r prime is for this problem. It's simply minus d over 2 I hat plus z k hat. And I need to know its magnitude. And that's just d squared over 4 plus z squared. And this entire quantity is taken to the 1/2 power. Okay. So I'm now in the position to write down an expression for the electric field due to Q1. So E1 is Q times minus D over 2 I hat plus K hat Z. So all this is upstairs in the numerator. And the denominator, I have my ubiquitous factor in electrostatics at 4 pi epsilon naught. And I have the quantity d squared over 4 plus z squared to the 3/2 power. And this is exactly what we got back in lecture 5. So it looks like if you write down this general expression for the electric field and you don't put the charge at the origin, you'll still get the same answer that we got previously. So how did we get the right answer? Using this expression, which I said was not applicable if you didn't have the charge at an origin. Well, what we did was, for r, we used the distance between where the charge was located and the field point. So even though we got off the beaten path and incorrectly used this formula for the electric field, which is only true if the charge were at the origin, we saved ourselves by using for r the distance between the charge and the field point. And in that example, in this example, that's just d squared over 4 plus z squared all to the 1/2 power. Okay. So we went backwards by one step, but we went forward by another. Okay, so the moral of the story is that we should be using, even though this is not going to really change anything that we've looked at in any of the examples, we should be using the general form of the electric field at some field point r. It is simply q r hat over 4 pi epsilon naught r minus r prime squared. Or if you choose not to have, you don't want to have your unit vectors flying around, get rid of them. Just that you have to renormalize or change that denominator to r minus r prime cubed. And note, so this is true in general, and note that if q is at the origin, namely if r prime is 0, then you get back the result that you would expect for the electric field of a single point charge. At 0, the origin. So the safe recommendation is start your electrostatics here. For that matter, start. The electric field is really just a form of Coulomb's law. So both of these guys really are in play for any choice of the origin. The origin does not have to be where a charge is. Okay, so to see this, it's probably useful to go back and look at some examples. See that all this is making sense. So we just looked at a case where we had two distinct point charges. So now let's look at an example where we want to calculate the electric field. Again, I'm repeating a problem that we've done before, where your charge distribution is not discrete, but is continuous. So I considered a finite wire of length 2L, which has a linear charge density, lambda, that of course has units of coulombs per meter. And what I wanted to do in this problem was in fact calculate the electric field at some point P, which was a distance Z from the origin. So this is a problem that we have done. Okay, there's a right triangle there. That's going to be very helpful. And geometry is going to tell me, or trigonometry is going to tell me that if I call the distance from the origin to this particular differential line element, dl prime, if I call that L, x, then the hypotenuse of this right triangle is just x squared plus z squared to the 1/2 power. Okay, so find, what do we want to do? We want to do what we did before. We want to find the electric field at the point P. Points are vectors, vectors are points. So how will we do this? Well, here I don't have a discrete system of charges. I have a continuous system of charges. So I have to add up the contributions of dE over some length. Now, if I want to break that integral up, Coulomb's law tells me that the numerator is just dq prime over times r hat divided by 4 pi epsilon naught, and the length of this vector r minus r prime. And again, it's going to be very helpful in doing this calculation to replace the unit vector in the numerator by a vector. You can do that. It just makes the denominator slightly different. Remember that r hat is just r minus r prime divided by its norm, length or magnitude. Let's give this guy a little bit more space so we can see exactly what's going on there. Okay, so our convention that we use in electrostatics is as follows. We will use prime variables when we're referring to the source, where the charge is. And we will use unprimed variables when we're referring to the position of the vector field. In other words, we want to know what the value of the electric field is at some point. So I've written my expression for the electric field in 3 different ways. I really want to use form number 3. And what I'm going to need, let me correct this. Form number 3 is r minus r prime upstairs in the numerator. I'm going to need to know what is, I know this line has a linear charge density lambda, so I don't need that anymore. I need to know what is r minus r prime. That's the key question we have to keep asking. Well, if you look at this diagram, r minus r prime is simply this vector. It's the hypotenuse of this right triangle. You can decompose it into its components. It has a minus I hat x. Remember, I'm using Cartesian coordinates here. It has another component, k hat, in the k hat direction, and its magnitude is z. And I'm in a position to get the final thing I need to know to solve this problem. I need to know the magnitude of that vector. That's easy. That's just x squared plus z squared to the 1/2 power. So if I go back, I now know what r minus r prime is for this example. I now know what the magnitude of r minus r prime is. I have to take this expression and raise it to the 3rd power. Hence, I get an expression in the denominator that goes like a quantity that goes to the 3/2 power. And this is exactly the same as what we got before. So the key question is, the key point is that if you're going to use this general form for the electric field, which is what we're going to do, you always have to be able to look at your system and ask, okay, what is r minus r prime? It's a vector, but what is it in relationship to the problem at hand? And then once you know it, you're good to go. You can calculate its magnitude, and you're off to the races. Okay. And the reason why we're using form 2 and 3 to calculate the electric field is that these expressions are valid anywhere, regardless of where you put the origin. And clearly, for this case of the continuous charge distribution, I have to pick a point to put the origin, but I have a finite wire of 2L. So, I can't uniquely specify where I'm going to put the origin. It could be anywhere. But if I put it here, then my expression is valid. So this is a much more powerful way of doing this. Okay, so you go from Coulomb's law to the definition of the electric field. You can calculate electric fields for discrete point charges. You can calculate electric fields for continuous point charges. We then, in electrostatics, looked at the idea of the electrostatic potential. And I remind you that this expression for the electrostatic potential, where here's an origin, here's a distance r, and my charge is located at the origin, so I'm calculating the electrostatic potential there. This is valid only if the charge is at the origin, which is very restrictive. What I'd like to do is write down a general expression for the electrostatic potential of a point charge, regardless of where I put the origin. I know how to do that. It's that. So again, here's my origin. Let me place a charge at some distance away from the origin. I need a vector to do that. That's going to be what I called my source vector, R prime. So I'll put a charge there. And then I want to ask, what is the electric potential, electrostatic potential at this point P, where P is denoted by my field vector. So field vectors are unprimed. R prime is a source vector. Source vectors have primes. That's the convention we've been using throughout this course. So now I see that I can define a vector that goes from my point P to the, well, in this case, it's going to go from the charge to the point where you want to evaluate the potential. Go in that direction. It's going to be R minus R prime. And that's exactly what I have here. All right, this is nice, but most of the time you do not in electrostatics have a problem where the potential is discrete, be continuous. Well, you know, we've dealt with these problems before. So you can have a continuous charge distribution. And in that case, all you have to do is not do a finite sum, but do an integral over dq prime 4 pi epsilon naught r minus r prime in the denominator. Note the beauty of the electrostatic potential is that I don't have to worry about vectors in the integrand anymore. I just have scalars. This thing is a scalar. And the only thing I have to worry about is calculating. I have to ask myself two questions. What is R minus R prime? And what is its magnitude? So I'm going to go through at least 2 examples of this. I should point out that if you are doing a problem, let's say where your charge distribution is 3-dimensional, then dq prime is rho prime. Well, dq prime is rho. There's no reason to prime rho. It's just simply a volume charge density divided by 4 pi epsilon naught. And again, my denominator has r minus r prime in it. So what's our convention? Primed variables tell us about the source of the charge. Unprimed variables tell us where the field vector is, the point in space where I want to calculate something, in this case, a electrostatic potential. Note when I do this integral, I integrate out over the prime coordinates, and I'm just left with an answer that just depends upon R, the source vector. So the source vector is R, source vector is the field vector. So the field vector is R, and the source vector is R prime. So this is my source. I'm integrating over. I also do that up here. And I'm left with my field vector, which just tells me what the electrostatic potential is. Okay, so we will go now and go back and revisit two problems we already talked about. So there's this general way of looking at the electrostatic potential, or for that matter, Gauss's, the electrostatic potential, or the electric field, or Coulomb's law. And in this general form, you don't have to put the charge at the origin. In some cases, you can't. So this is why this general form is useful. So let's go back and look at this problem again, revisit it. I'll have two charges, Q and Q sub 1 and Q sub 2. They're both the same. Here's an origin. So these two charges are located at a distance d over 2 from the origin. And let's just worry about doing half of the problem. Here's a distance z, here's a point P. And what I want to do in this problem is find the electrostatic potential at point P due to Q sub 1. So you can see immediately why the electrostatic potential is a much more easier thing to deal with rather than calculating electric fields. All you have to do is calculate the electrostatic potential and take minus its gradient, and that gives you the electric field. So the general form is just Q sub 1 over 4 pi epsilon naught divided by R minus R prime. This thing on the left-hand side is a scalar. So all I have to do in this problem is figure out what R minus R prime is and figure out what its magnitude is. That's pretty easy to do. Let me draw another figure. I don't have to draw on the original figure. These guys are right triangles. Here's my origin. Here's my charge Q sub 1. Here is my source vector, R prime. Points from the origin to Q sub 1. Here's my field vector, R. It points from the origin to the point where you want to evaluate the electrostatic potential. And that, in this example, that's the point P. Vectors are points, points are vectors. So this vector is the distance between Q sub 1. You start at Q sub 1 and you end up at the point where you want to calculate or evaluate or measure the electrostatic potential. And so it's got to be the vector R minus R prime. And if you look at this diagram, z squared plus d squared over 4 taken to the 1/2 power is exactly the magnitude of R minus R prime. So you're good to go. You just have to write this out. What is this vector, R minus R prime? It is simply, we've seen this before, I hat x plus j hat z, or in this particular example, R minus R prime is just minus I hat d over 2 plus k hat z. So what you'll need in the denominator is the norm, magnitude, or length of that vector, and that's just going to be d squared over 4 plus z squared all to the 1/2 power. So I want to calculate the electrostatic potential due to charge 1, Q sub 1, in this particular diagram. I just need to know what this denominator is. There it is. In terms of the parameters in the system, D and Z. This is exactly what we got before. So again, even though I take this general approach to writing down Coulomb's law or the electric field or the electric potential, I still get the same answer that I got before. Okay, let's look at a final example of this. Let's consider a uniformly charged spherical shell of radius r. So we have done this problem before. We're just going to revisit it. So there's my shell. It would stand to reason that this is a problem I want to solve in spherical polar coordinates. That would be a reasonable assumption. So the first thing I'm going to do is recognize that I have a differential surface element, ds, that is located a distance r from the origin of this system. Here are my obligatory unit vectors, I hat, k hat, j hat. There is an angle that r makes with the z-axis. We'll call that theta prime. And then there's a vector that goes from ds, the prime, the differential surface element, to some point on the x-axis. And let's call that point on the x-axis P. So given this system, what we want to do is find the electrostatic potential at point P. So again, we can write down a general expression for the electrostatic potential. It's going to be 1 over 4 pi epsilon naught times an integral over dq, and I have the magnitude of the vector r minus r prime in the denominator. Now, this system involves doing a surface integral. So I have a surface charge density sigma, and I have a differential surface element ds upstairs. And then I have my 1 over r minus r prime downstairs. So, 2 things at a time, or 2 things I need to do. Sigma is going to be a constant in this problem, so it just comes out of the integral. ds prime, again, I prime all of my sources of charge in spherical polar coordinates. Since I'm looking at a shell and not a sphere, it's just r squared sine theta prime d theta prime d phi. So I know how to tackle the numerator in this integral. The remaining task is, what's the denominator? So I need to find out what r minus r prime is, and then figure out what its magnitude is. So I'm going to do that by taking out of this figure a triangle. This triangle is not necessarily, it's definitely not a right triangle. Here's the origin of this triangle. One side is z, one side is r, and here is the distance between d sub s prime and z. And so that's what I want to figure out what it is. So let's do that here. So here's my origin. Here's Z, and here's big R. Well, this is equivalent. Remember, here's a point in space that you want to calculate the electrostatic potential, and here's ds prime where the charge is. So let's use the prescription we've been using up to now. This is, starting here at the origin, this is the vector r prime. It's the source vector. It goes from the origin to where charge is located on the surface of the charge. Here is the position vector, r. It is what I want to do when I want to find out where I want to calculate the electrostatic potential. So P is there. So the vector that goes from the charge element, designated by dq prime, which is sigma ds prime, is just this vector. It's r minus r prime. We used our friendly law of cosines, figure out what that was, and that's simply z squared plus r squared minus 2z r cosine theta. And the rest of this is exactly the same. As before. And again, the beautiful thing about the electrostatic potential is when you evaluate the integral, it's much easier to do. It just involves scalars, not vectors. So I'll just write down what we've discovered, the electrostatic potential for this problem, which we've done by using this general definition for the electrostatic potential as a constant. Surface charge density comes out of the integral, and I essentially have to do a two-dimensional integral. The numerator has r squared sine theta d theta d phi, and the denominator is r squared plus z squared minus z r cosine theta prime. All of that to the 1/2 power. No 3/2 here. Okay. Primed variables tell me where the charge is. Unprimed variables tell me where the source is. R is a constant. I do this double integral, so it's a surface integral. I integrate out all of the primed variables, and I'm just left with something that depends upon z. And we have done this before. So in summary, our general expression, or expressions plural, for the force in Coulomb's law, the electric field, and the electrostatic potential are extremely useful to take advantage of because they're independent of the origin. You don't have to specify the charge reside at the origin or anywhere in space for that matter. Okay, so as advertised, I wanted to make a few comments on magnetism, and in particular, magnetostatics. And by no means, shape or form is this discussion going to be all that comprehensive. It's just going to give you a glimpse as to what's going on. Okay, the problem that we have to face now is that when we're talking about charge, we've always assumed that charges were stationary or fixed. And we know in real life that's not true. Charges move. So in fact, you can define something called the current, and I'll use this symbol capital I for current, so I don't confuse this with the imaginary number I hat from our discussion of vector analysis. My current is going to have units of how much charge pass a point in space per unit time, and that's going to be defined in terms of a unit called an ampere. So current also can be written as a linear charge density, lambda, times a velocity. And this is easy to see. Linear charge density has units of coulombs per meters. Velocity is something that has units of length over time. So this final creature, again, is going to be an amp. Current is going to be something that has units of how much charge passes a point in space per unit time. Now, current, you may not be used to thinking about this, but current is actually a vector. It has a magnitude and it has a direction. Just as velocity and speed are two different things. Speed is the norm of the velocity vector. So the proportionality constant between the current, I, and the velocity of a charge is just the linear charge density, lambda. And one last thing we can see out of all of this is that since charge is just, or current is just the time derivative of charge, a small piece of charge, dq, is just going to be given by I dt. That's simply the linear charge density times v times dt, but a velocity times time is a length. So a small piece of charge is just a linear charge density times a differential length. So all these are dimensional analysis arguments. So dimensional analysis is a tool that you've used thousands of times already in all your studies, and it's extremely valuable because it allows you to keep all these things together. Okay, so I've got this formalism set up, so let me do an experiment. So the experiment I'm going to do is I'm going to have a wire, which I'll call wire Roman numeral 1, and through that wire there's some current. And remember I said current is a vector, so I have to specify the direction. So the experiment I'm going to do is I'm going to construct a second wire, which I'll call wire Roman numeral 2, and it will have a current that points in the same, goes in the same direction. So the remarkable result of setting up this experiment is that these wires, now that I have a current running through them in the direction specified, they attract each other. This is a remarkable experiment. And there's no way in the world that I can explain this experiment by using anything we've talked about in the previous 12 lectures. Electrostatics is not going to help me. So what is going on Clearly, if I turn off the current, this force disappears and the wires are fine. But if I turn on these two currents and they go in the same direction, excuse me, then these wires will attract each other. So at least experimentally, I can say that there's some force between these that a wire experiences. Force is a vector. And that force has something to do with current. But again, current is a vector. And I need to do a better job of pinning this guy down. And also, current has something to do with how fast charges move. So it has something to do with velocity. Now I'll give you one more exciting piece of this experiment. If you come along and place a stationary charge, Q, and put it right there, just nail it down, or just place it right here, it's not going to be affected in this experiment. So if you turn off the current that goes through wire 1 and wire 2, nothing happens. I just have a charge in between the two. And then if I turn on those currents, those wires are going to be attracted to each other, but nothing's going to happen to that charge Q. So there's something going on that has nothing to do with electric fields that you would think about. I mean, the stationary point charge Q is not going to generate an electric field, but it's just one more piece to the puzzle. So let's see if we can figure out what's happening in this experiment. Let's go back to the experiment and analyze it very carefully. So here is my wire 1. Again, current is a vector, so I have to specify the direction of the current going through wire 1. And I'm going to ignore, let's say, anything about the dimensions of the wire. It's just infinitely thin. I don't want to make the experiment, I don't want to make the model too complicated. But the experimental reality is that this works for real wires. So if I ignore wire, well, let me consider wire 2. Let's say it's there. Probably there's no reason to put this, to give this a dashed life, so it has a real life. What happens is that this wire 2 gets attracted to wire 1. So there's some force which I can designate by a vector. And let's call that vector a force. So let's pull out of the diagram. I have a vector F, and I have a velocity vector that describes charges moving in that wire. So clearly, something is going on in this problem. The particles or electrons moving in wire 2 don't see a force that's in the same direction as V. They see a force that's perpendicular, at least, to V. So what's the source, what's the origin of this force? Well, it turns out that wire 1 will generate everywhere in space a new vector field. It's not electromagnetic, or it's not electrostatic in nature at all. It's something we'll call the magnetic field. Give it the symbol B. And note that One of the reasons why we spend so much time doing vector analysis is that we're now in a position to realize that this force obeys a very simple relationship between V and B. Namely, the force is given by the cross product of V and B using our friend, the right-hand rule. Okay. So when you take V and cross it into B, you get a force that points in that direction. Now that tells you something else. That tells you that this magnetic field B points in that direction with regard to wire 2, and actually tells you something even more powerful. Let's call this the end of wire 1, and let's call this the front of wire 1. And let's look down the end of wire 1, and we'll note that by an X. What we are saying is that if you go away from wire 1 by some distance, you will see a new vector field generated by the fact that you have a current going through that wire. And that new vector field points in that direction. We'll call it P, B. But there's symmetry in this problem, right? There's nothing special about this particular point. I could look at points all described by this circle. And at every point, there's going to be a vector field B. And what I've discovered is for this experiment to work, for wire 2 to be attracted to wire 1, there's got to be a magnetic field B that goes around the wire in a clockwise direction. If you look down the end of wire 1. Okay. The force that wire 2 experiences is given by this relationship. It's not B cross V, it's V cross B. And again, inside wire 2, there has to be something that's associated with these particles that are moving. These particles that are moving inside wire 1, they all have a charge. There's a current inside wire 1, a current inside wire 1, and there's a current inside wire 2. And wire 2 is going to feel a force that's dependent upon the field B generated by wire 1 and the velocity of particles moving inside wire 2. Okay, let's take a deep breath. So we claim that this experiment can only result with the introduction of a new vector field called the magnetic field. This magnetic field only occurs when you have current being generated. You turn off a current, there's no magnetic field being generated. This magnetic field has a very special property such that when you act on particles of charge that are moving, you cause them to experience a force that's not linear, but depends upon the direction, cross product of the velocity of the particle and the magnetic field. So the remaining thing needs to be done. Well, let's back up a minute. So what does, if all this is actually true and not science fiction, you could ask the question, what does the magnetic field look like if this expression is going to be true, and if in that previous experiment the wires have to attract each other? I mean, you got to explain the experiment somehow, okay? It's not magic, not magical gremlins that come along and pull those two wires together. And it's not Coulomb that's doing it. It's not Gauss that's doing it. So if you look down the edge of that wire and you pass a current that goes, so the current I goes into, remember currents are vectors, it goes into the plane of my whiteboard that I'm writing on. So given that geometry, what we're claiming is that this current generates a vector field that looks like this. It's constant along a certain radius of a circle that circles the wire. And the direction of these field vectors is such that it is clockwise. If you want to explain the experiment, here's an hypothesis. Okay, so we think this is right, or if we think this is right, let's do a second experiment. The second experiment I want to do is go back to my wire 1 and have a current going through it. Again, I have to specify the direction for a current. Current is a vector. Now I have a wire 2 in my system, but I will set it up so that the direction of the current in this wire is anti-parallel to the direction of the current in wire 1. So the currents in this experiment are anti-parallel. So I'm going to work backwards. I'm going to assume that I believe this expression. And then I'm going to ask myself, if I believe this expression, what is going to happen in this system? What's going to happen between these two wires if their currents are anti-parallel to each other? Okay, so I think we're in a position to answer that. Let's start over here. First things first, my wire 1, I claim, generates a real magnetic field. For the reasons that we just talked about, as far as wire 2 is concerned, this magnetic field points downward. Remember, if you look down the edge of the end of wire 1, In the previous case, we claim, and we pass a current down that wire, we claim that a vector field is generated. That vector field has nothing to do with the electric field. It's a new field called the magnetic field. We actually won't talk about how to calculate it here, but we know how to, but we've discovered it has a direction. And that direction in this orientation is clockwise. So in fact, let me draw this diagram a little differently. So B will go in that direction. V is the direction of the current. Remember, current and velocity are both vectors, and they both have the same direction. So now my rule or law that I've derived from the previous experiment tells me that there'll be a force on wire 2 due to the magnetic field generated by wire 1. And all I have to do is calculate, use this expression to figure out the direction of that force using the right-hand rule, which would be a force in that direction. What that's going to tell me is that for this system, wire 2 will experience a force due to wire 1 that points in that direction because the wire 2 has a current that's anti-parallel to wire 1. And you could reverse this argument. You could do it for looking at the magnetic field generated by wire 2 acting on wire 1, and you'll see a force in that direction. So if you believe this guy, it's going to make the prediction that if you reverse the direction of the currents in wire 1 and 2 so that they're anti-parallel, you'll see a repulsive force. The wires will repel. And, wait for it, this is what the experiment reveals. So, other than using the invention of microscopic gremlins, you can say that the way to explain these two experimental results is by this expression, which is quite complicated. I have to define what I mean by quite. It's more complicated than Coulomb's law. Coulomb's law says that if you have a charge in the presence of an electric field, then that force, that electric field creates a force F on that particle, and the direction of that force is the same as the direction of the electric field vector. This experiment says that if you have a moving charge, Q, with some velocity V, inside some current on a wire, that magnetic field will exert a force on the moving charged particle or on the current, and that force has a direction given by the right-hand rule. So you can combine these two things together and recognize the following observation, which in fact turns out to be experimentally true. So I haven't derived these guys, I've just shown that they explain experiments. First 12 lectures, we know what the electric force is on a charged particle due to an electric field. What we've discovered now is to at least explain the experimental situation where charged wires that have currents in them that are parallel attract each other, and two charged parallel wires that have currents in them that are anti-parallel to each other have a force that's repulsive. And this combined force is something we'll call the Lorentz force. Okay, so we need, in summary, more than just the electric field, explaining things that are going on in nature. The electric field really comes from charges that are stationary or fixed. Once charges move, you generate currents. And these currents generate a new type of field that's different, completely different than the electric field. That field is something called the magnetic field. So magnetic field. So steady currents, currents that don't change in time, generate magnetic fields. Obviously, you could ask the question, what happens if the current changes in time? Suppose you go from a DC situation to an AC situation. There are a whole host of issues and problems that are before us. Are the electric field and the magnetic field all that different from each other? Is there a relationship between the two of them? Can they get together and sit down at a table and do something and produce something even more exciting? Light, electromagnetic radiation, devices, circuits, antennas. All of these questions are important questions to raise, and you'll see them discussed in future courses in electromagnetic theory. So that ends our discussion of lecture 13. It ends our discussion of how vector analysis, multivariable calculus, and vector calculus are crucial to being able to solve problems, elementary problems, but challenging problems in both electrostatics, and also I've tried to give you a glimpse that these same tools are useful to describe the magnetic field or problems in magnetostatics. So that will end today's lecture. Thank you very much for your attention.